Hello, today I'm going to provide an update on the Extreme Precision Radial Velocity Initiative Working Group. My name is Scott Gaudi. I'm co-chair of this working group along with Gary Blackwood, and I'm giving this presentation on behalf of NASA's Exoplanet Exploration Program and the entire EPRV working group. Okay, so here's a brief outline of the talk. First, I'm going to give a motivation for why we want to pursue extreme precision radial velocities. Then I'll talk about the current state of the art. Then I will go on to talk about the methodology about how our working group achieved its recommendations. And I'll talk a little bit about our architecture simulations, which provided proof of concept that should we be able to mitigate sources of systematic errors, we would be able to detect and characterize Earth analogs around nearby sun-like stars. And then I'll talk about the proposed research program that needs to happen before such a survey could actually begin. So let me begin by talking about the motivation for extreme precision radial velocities. In other words, why do we need to measure the masses of Earth-like planets orbiting nearby sun-like stars? Well, as quoted here in the National Academy of Sciences Exoplanet Survey Strategy Report, mass is the most fundamental property of a planet, and knowledge of a planet's mass, along with the knowledge of its radius, is essential to understanding its bulk composition and interpreting its spectroscopic features and atmosphere. If we seek to study Earth-like planets around sun-like stars, we need to push mass measurements to the sensitivity required to detect such worlds with precision radial velocity. So why precision radial velocity? As I like to say, learn it, love it, use it. This is, I think, a nearly airtight argument as for why we should start pursuing extreme precision radial velocity initiatives today. So as we said, we need to measure the masses of directly imaged habitable planets around nearby stars, as well as the masses of rocky terrestrial transiting planets. We have two choices to be able to do this. One is astrometry with a systematic floor of a few tens of nanoarcseconds, or radial velocity with a systematic floor of a few centimeters per second. Astrometry is universally acknowledged that must be done from space, at least at this level of accuracy. And so that likely would require a greater than $1 billion dedicated mission, or perhaps a specially designed instrument on another large aperture space telescope, such as LUVOIR, could do this, but it would still be expensive, several $100 million, and would require significant technology development, and of course, you would need a mission as well. On the other hand, extreme precision radial velocity at a few centimeters per second may be doable from the ground. Now, I realize this is a controversial statement. Some people will tell you it's impossible. This may well be true, but we do not know this yet. It is an opinion, not a demonstrated fact. In fact, some recent radial velocity stellar activity work has shown very promising signs of mitigating stellar activity at close to the levels needed to detect Earth analogs around nearby sun-like stars. If we can do this from the ground, it would almost certainly be cheaper than any other option. So thus, given that we should first try what is likely to be the cheapest option and see if it works, we should perform the needed RNA to determine if we can achieve this few centimeters per second accuracy. And if we can do this from the ground, we can dramatically improve the efficiency of direct imaging missions, and as well as perhaps increase their yield. So, what is the effect of precursor observations on direct imaging missions? Precursor observations generally help if the time to detect a planet is much greater than the time to characterize it. For example, if you have low completeness per visit, in which case you might have, for example, a very small dark hole or a large interworking angle, or if eta Earth is very small. On the other hand, if the yield is resource limited, in other words, you have a limited number of slews for a star shade or long integration times required for characterization, in that case, precursor observations can dramatically improve your efficiency, allowing time for other science and also mitigating risk. And in certain circumstances, can also improve the yield of characterized planets. So that's demonstrated here. This is a plot by Rhonda Morgan using the ExoSims tool. This just shows the number of Earth candidates on the y-axis that are characterized. On the x-axis is mission duration in days. The blue curve is with perfect precursor knowledge. And you can see we reach 50% yield at slightly less than 200 days. The red curve is with no precursor knowledge, in other words, a blind survey, and we reach 50% yield at over 600 days. So in other words, you can require 3 times the amount of observing time to reach the same yield of detected and characterized planets with a blind survey than if you have a perfect precursor knowledge. This means that high impact science occurs earlier in the mission, allowing more time for follow-up and characterization. You get more immediate science results that excite the public and science community, and of course you mitigate a risk of early mission failure. So extreme precision radial velocity missions make, precision radial velocity makes missions more powerful and nimble, and they ensure that you have the targets on day 1 to observe and characterize. So what's the problem? Well, as documented very well in Fisher et al. And Dumusk et al. 2016, there was a community-wide data challenge initiated by Xavier Dumusk, in which he inserted signals into radial velocity time series, and then gave those signals to the best EPRV modelers and statisticians in the world to see if they could recover those signals. And the primary conclusion of this data challenge was that even with the best models of stellar signals, planetary signals with amplitudes less than about 1 meter per second are rarely extracted correctly with current precision and current techniques. And you can look at the radial velocity amplitude of detected planets with radial velocity, and you can see that we've been stuck at basically 1 meter per second for the last decade. So in other words, if we must do something fundamentally different than we have been doing to achieve the 10 centimeter per second precision and 1 centimeter per second accuracy to detect and characterize Earth-like planets around nearby sun-like stars. So this led to the following recommendation from the National Academy of Sciences Exoplanet Survey Strategy. The main recommendation is improving the precision of radial velocity measurements in support of exoplanet missions. There were a number of findings, which I won't read. I'll just read the recommendation. NASA and NSF should establish a strategic initiative in extremely precise radial velocities to develop methods and facilities for measuring the masses of temperate terrestrial planets orbiting sun-like stars. And why NASA and NSF? Well, NASA is very good at running missions from the top-down kind of organization, and NSF excels at running ground-based observatories. So together they can play to their strengths to achieve this initiative. So why 10 centimeters per second and 1 centimeter per second accuracy? Well, the RV amplitude of an Earth analog around a nearby sun-like star is roughly 10 centimeters per second. And single measurement precisions are going to be at roughly that level. They're not going to be considerably better than that. So if you want to detect an Earth analog at a signal-to-noise ratio of 10, this implies a mass measurement of 10%, then you need roughly 250 measurements with single measurement precision of 10 centimeters per second. And they must beat down by root n. So this requires systematic accuracy of a few centimeters per second. And you can see that here in this figure, which shows a simulated radial velocity data set, phase folded at 1 year period. You can see the individual measurements have uncertainties that are much larger than 1 or 10 centimeters per second, but they average down to the red points, which follow the 10 centimeter per second curve quite well. And this is simulations done by Patrick Newman and Peter Plotjon at George Mason University. So the problems are both the known unknowns, and the more scary unknown unknowns. So the problem from going from 10 meters per second to 1 meter per second were a number of unidentified errors like stellar activity. The problem of going from 1 meter per second, where we are now, to 10 centimeters per second is the number of unanticipated and uncharacterized errors. And it's almost true that when we start to go below 10 centimeters per second, we will encounter a number of unanticipated terms in the error budget that we will need to address. And in some cases, we may not even have the right tools to address them. So what is the current state of the art? Well, this is just a subset of facilities that are online, have recently come online, or will be coming online in the future, that hope to achieve accuracies of a few tens of centimeters per second up to maybe 50 centimeters per second. And so I won't mention these in specific, but some of them are newly made instruments designed to have very low systematic instrumental systematics, and should be able to achieve these sub tens of centimeters per second accuracy with sufficient cadence and observing time. So the challenge, of course, that we face, amongst others, is stellar variability. So this is a blanket term for lots of different stellar effects on the photosphere of the star. This includes P modes, granulation, which operate on timescales of a few minutes, supergranulation, which operates on timescales of a day, R modes, faculae spots, which operate on timescales of the rotation period of the star, or roughly a month, and then magnetic fields and magnetic cycles that operate on timescales of years. And you can see that a lot of these effects are basically at the 1 meter per second level. And so we have to turn these systematic uncertainties into signals so that we can remove them to detect the signal of an Earth at 1 year and 10 centimeters per second. So this was the methodology of the EPRV working group. We established terms of reference, membership, and ground rules. The membership was open, and the documents were accessible via Google Drive folder. We formed an EPRV working group of about 36 of the world's experts in various topics, such as instrumentation, stellar activity, statistics, etc. We established 8 subgroups. We had bi-weekly telecons, and each group formulated research recommendations. We also held 3 face-to-face multi-day workshops in St. Louis, New York, and Washington. And in general, we use the Kepner-Trigo method to develop a architecture or architectures which could, if we mitigate the sources of systematic error, could actually detect and characterize Earth analogs around nearby sun-like stars. So we formulated a decision statement, formulated success criteria, formulated candidate architectures, and conducted weighted trade studies that counted for risks. And as a result, we established existence proofs that the EPRV objective could be achieved if we mitigated these sources of systematics. And full consensus of the working group was achieved. We also had a red team review, and we had an EXOTAC briefing. So these are the working groups. I won't go through them all, but you can see that they span a broad range of topics, from instrumentation and calibration to intrinsic stellar variability, survey strategy, statistical inference, pipelines and analysis, telluric mitigation strategies, and instrument performance evaluations, etc. So each of these groups worked very hard and came up with recommendations. And we arrived, the working group, by consensus at the following decision statement. That is, we wanted to recommend the best ground-based program architecture and accompanying research and development focus areas to achieve the goal of measuring the masses of Earth analogs orbiting sun-like stars. So with the Kepner-Trigo methodology, we identified 6 musts, which I won't read here, but you can read yourself. These are gates that must be passed by any architecture before it is considered viable. And then we also identified 4 wants to discriminate against those architectures that pass the musts, to decide which one we thought was the best architecture or architectures. Briefly, I'll just discuss the proposed architectures. But first, I'll talk about the target stars. Obviously, we need to know what the target stars are that these architectures are going to be surveying for Earth analogs. And we compiled 2 target lists based on agglomerating the LUVOIR, HABEX, and Starshade rendezvous star lists. There was a green set of stars. These are sun-like stars with relatively small projected rotation velocities of less than 5 kilometers per second, and that were on at least 2 mission study lists. And then the more difficult yellow stars, which were also sun-like stars with slightly higher projected rotation velocities, or were only on one mission study list. The architectures vary widely in terms of the aperture, number of telescopes. We even had hybrid architectures with multiple apertures. Here, we just show schematically the different architectures we considered. I'm going to just, as an example, focus on one, architecture 1, which considered 6 2.4 meter telescopes. In order to survey all the stars which are distributed around the sky more or less uniformly, we had to have these telescopes longitudinally and latitudinally distributed all over the world. We considered these telescopes to be basically identical, the instruments to be, and telescopes to be identical clones of each other, thus enabling more uniformity in the data collection and analysis. The wavelength coverage was roughly 0.38 to 0.93 microns, a spectral resolution of at least 150,000, a total system efficiency of 7%, instrumental noise floor of 10 centimeters per second, and these would all be dedicated. And they would also include solar full disk telescopes as well. So with these architectures, we simulated things like weather, the instrument design, the desired RV precision and signal to noise, put them in a simulated dispatch scheduler, and then came up with observing logs, targets, dates, times, and the resultant RV precision, et cetera. And so this is a kind of result of a typical one of these simulations. This shows the number of stars in the target list as a function of the signal to noise of Earth analog detected based on some number of observations. And so we required that the signal to noise be at least 10 so that we get a mass measurement of at least 10%. And in the case of architecture 1, the median signal to noise ratio is about 21. And the 10th and 90th percentile varied from about 17 to 33 in terms of signal to noise ratio. This says that if there were an Earth analog around each star, and if we were able to completely remove the star's variability from our RV data, then this would be the significance of the detection of the Earth analogs around each one of the stars. Okay, so we did the same for all the architectures. This shows the basic results. You can see that they differ in detail, but in general, for all the architectures and almost all of the target stars, they reach this minimum signal to noise of at least 10. So that means that we have existence proof that there's a variety of architectures that pass our musts and can be considered viable. So again, we evaluated each of these architectures against our musts to make sure that they passed all of our musts. And then we evaluated them against our wants, and then also included possible risks. And so given these existence proofs that should we be able to mitigate these sources of systematics, that we could achieve the signal to noise ratio with the cadence and Poisson noise to achieve the detection at a signal to noise of 10. We then need to understand exactly what we needed to do to mitigate the stellar variability, systematics, tellurics, et cetera. And so we concluded that one of the most promising ways of trying to understand stellar activity, which is, as I said, a blanket term for many different effects, as listed here, probably the best way to at least start this process is to actually observe integrated disk observations of the sun on a daily or even higher cadence basis. And that would allow us to try to, especially at high resolution, this would allow us to disentangle these various sources of systematics, turn them into signals, and thus remove them so that we can get to the statistical precision of the data themselves. So we also considered requirements for the data reduction pipeline. I won't go into these in particular, but we thought about these very carefully and categorized them in terms of bare minimum, strongly recommended, and bonus properties of these data reduction pipelines. We also considered technology development. So these fell into categories like calibration of the spectra, so that we know what wavelengths correspond to what absolute wavelength correspond to what spectral lines. the systematics in the detector, because these can cause deviations of the 10 centimeters per second quite easily, gratings, the fiber front end, and adaptive optics. So we considered the possibility of using single mode fibers, AO single mode fiber instruments, which would be smaller, more compact, and easier to build. That was our basic conclusions. And like I said, as a result, we came up with a suggested RNA program. You can see the results listed here. And I just wanted to announce that that there will be a new ROSES 2020 solicitation coming in support of our conclusions. This is called the Extreme Precision Radio Velocity Supporting Research and Technology Development. The expected timeline for this call is sometime in August. Proposals will be due in the November to December timeframe. Selections will be announced in spring of 2021, and 2-year awards will be fully funded in FY21 for a total of $1.5 million, roughly. So this represents an initial response to the recommendations of our working group, and will be focused likely on the tallest tentpole items. And we hope to continue and expand the scope of this program contingent upon recommendations of the ASTRO 2020 Decadal Survey. And with that, I will take questions. Thank you.